Thank you. It's nice to be here. So my name is Anthony Talamantes. I'm a senior manager at Johns Hopkins University of Cybersecurity Operations, primarily. I'm going to be representing operational cyber research that we do here at the lab. I am going to do a little bit of background on the organization just to clear up some confusion. We're going to talk a little bit about SIEMs. We're going to do some things that you can't do with SIEMs so much, and then we're going to get into a little bit of machine learning, and then look at the data once we've applied some outlier algorithms to the data. First of all, Johns Hopkins University Applied Physics Laboratory. Sometimes I'll refer to us as APL. So if I say APL, don't get confused. We are not part of the university. We are a U.S. defense contractor. We do work for the DoD, NASA, DHS, the Intel community. NASA, if you think about, if you heard about the DART spacecraft that flew into an asteroid to change its trajectory, that was us. Kind of fun stuff to work around, but that's who we are. We have an affiliation with the university, but we're not part of the university. Being a defense contractor, we get targeted by some of the more sophisticated threats. In 2009, we were compromised by a nation-state adversary. We made the papers. It's not how you want to make the papers, but we did. We were actually disconnected from the internet for 2 full weeks while we cleaned up the situation. I wasn't there in 2009, but irony is I worked for another defense contractor that was compromised by the same nation-state adversary, so I was very familiar with them. They are now defunct because there was a U.S. indictment on the individuals that were involved with that. 2014, if we remember the Heartbleed incident, and these slides will be released. There's an article there, a Mandiant, about the type of activities this adversary did, but they were able to exploit the vulnerabilities, pull memory down, and then grab session keys, and then reestablish sessions to the appliance. They exploited and reestablished session keys, which was a fun incident to be a part of. But both of these were advanced persistent threats that were tied to nation states. Just to give you a little bit of a background of the types of things, the types of adversaries that we deal with here at the lab. And as I talk about behavioral analysis, and I talk about sophisticated adversaries, this is what I want you to keep in mind at least. So in 2014, I created our operational cyber research based on 4 components: researching the adversaries, emulating them in our environment, mostly under an assumed breach methodology, engineering solutions, and then developing and applying analytics. It's a continual process, but this is the process I created here back in 2014 when I started at the lab. So what I want to start off with is I want to go back 10 years. This is from a presentation I gave 10 years ago. I did some research, and I had noticed an anomaly in Mimikatz. It's interesting that they had required fields and optional fields when you configured a golden ticket. One, optional, the required field of account name and the optional field of the RID of the user. Now I've broken down the SID here on the right-hand side, and the last digits is the RID. And so think 500 is the built-in administrator account. That's the RID. So the interesting thing about Mimikatz is if you do not fill in the RID, it will automatically populate it with 500. So either one of two things happens. You renamed your administrator account, hopefully. You'll have a mismatch between whatever account name they used and the actual security ID as it resolves within Active Directory. If they pasted it wrong, then you'll have a mismatch. We call this the lazy adversary, or we also call it the adversary that doesn't think the blue team's good enough to find these nuances in logs. But the point of this is the code here at the bottom is fairly high fidelity. This rarely happens in an environment. And with just a few lines of code, we were able to create a high fidelity alert. And that was 10 years ago. And things have changed. Today, when we look at queries, now this is not really a real query. I just want to kind of demonstrate what our queries look like today. And some of them are even bigger than this. And they time out, or they don't work, or we're joining too much data. And that's one of the things I did several years ago is I took a step back and I said, hey, why are we using a SIEM to analyze all this data? And we had data all over the place. We had data in SQL tables. We were pulling data from APIs. We had, data in SaaS solutions. And we couldn't actually afford to put all of our data in our SIEM. So we're having to make decisions where to put certain types of data. And I was also looking at the types of things we were doing with our data. And I thought to myself, what are other industries using? I mean, why is this just a cyber problem? Like, what is marketing, business, and finance? What are they using to analyze their data? They're not using SIEMs. Why are we using a SIEM? And I mean, there's several things. It comes with content. It's a central alert repository. Maybe your cybersecurity workflow works with it. But there's just a lot of things that it doesn't do. It doesn't help with anomaly detection, exploratory data analysis, and I'm going to get into that in a few slides. But one of the things that was common in the industry was Python, Pandas, working in Jupyter notebooks, using with Scikit-Learn was fairly common within the other industries outside of cyber, and it just wasn't adopted quite like it was in other industries. I have ideas. I think people are generally cybersecurity are afraid of moving to a tool that's focused on Python, where they have to actually create code. And I'll kind of go over that. I think people just in general get a little intimidated when thinking about applying data science to cybersecurity problems. But one of the things with Python and using Pandas is we get stateful analysis. There's this idea with a SIEM that you got to put this biggest query together to get the output that you want because you got one shot. If you get 10,000 results, what do you do with those 10,000 results, right? You can export it, maybe do some massaging, import it, put it in a table somewhere. But with Python, you do stateful analysis. That data is in memory, and then you can reuse that data in a different way. And I'm going to go through some examples. Unlimited data operations. You can transfer, merge, pivot on data, create loops. If you got too much data that came back, you can send in batches in a loop. And then also you can create reproducible workflows. We primarily do it in VS Code or Jupyter notebooks. And then what we end up, and what the graph on the right kind of represents, is we end up having these buckets or tables, or however you want to refer to it, of data that we can then, I look at it as a bunch of Venn diagrams, and we're looking for an overlap of data analysis within the Venn diagrams. So with this example, what we're going to do is we're going to start with some raw data. We're going to do a little bit of feature engineering. Maybe we're going to think a little bit differently about the data that we have, the raw data that we have. We're going to do a little data conversion, and then we're going to apply some machine learning algorithms to it. We're going to have some results, and then that'll go into one of those buckets. So the first thing is we have 3 different columns. We have app, so this defines, if I didn't say it, this is identity data. So within our identity data, we have the app that we're authenticating to. We have the event type, so sign on, start. You can think of that, and then we have the outcome, which is deny, failure. And individually, what I want to do is I want to use these as features. And I'm going to show you how we're going to do that. But what I want to do is I want to create a new field. I want to create a field that concatenates these fields together. And there's a little bit of code there at the top. Just a little bit of Python helps us there. And what I do is I create this new field. It's called triplet, and it encompasses both the app, the event type, and the outcome result. And why do I want to do this? Because I'm going to use those as features. And if I use each app as a feature in and of itself, we'll take the first row, and this is a slice of data that we have, and all of these things happen for this user, but we don't know if we take that top row, we don't know if that one under success is related to Dropbox or if it's related to Salesforce. We don't know if that one under failure is associated with a login or a log off. But when we put them together in a triplet, then we have the actual context. So again, we're kind of thinking creatively about how we can do some analysis on this data. The second thing I'm going to do is I'm going to slice the data up. So I'm going to take 90 days worth of data. And I don't want something that happened 90 days ago to impact or affect analysis that happened within the last couple of days. So what I'm going to do is I'm going to take slices of 3 days. So say Monday, Tuesday, Wednesday. Then I'm going to overlap 48 hours and increment that by 1 day. So I'm going to take another slice, Tuesday, Wednesday, Thursday, so on and so forth for that entire set of 90 days. Because what I want to do is I want to analyze anomalies for small snippets of time. Now, I didn't start with 3 days. I experimented. Experimentation is a huge part of applying data science techniques. I could see going further, thinking about maybe a more stealthy adversary and wanting to expand over, a 7-day period of time. I actually tried 1 day, 2 days, 5 days. 3 days seemed to be a sweet spot for the application that I was applying this to. And then, so once I did that, you see the list of triplets that we have here on the left-hand side. And again, I'm using Scikit-Learn. There's a library in there at the top, 3 lines of code. Really, guys, the code's like the easiest part. I mean, that's simple. It's like coming up with the ideas and getting to know the data. But what I want to do is I want to flip all those triplets, pivot, like a pivot table, and move those into its individual columns so they become features. So there's 121 different combinations of triplets. So I end up with 121 binary features that I'm going to be using in doing some more data analysis. And now we have our features as numbers, and we can apply some machine learning to it. And again, this gives us ability to analyze smaller increments of time and establish a baseline over the past. Okay. First thing, I'm not a data scientist. I've been in cybersecurity for over 20 years. I've been working for defense contractors for over 16 years. I've installed ArcSight back in like 2007 and used, every SIEM under the umbrella, under the sun. But I luckily have a data scientist on my team. I can run really bad ideas across, and he can say, "No, Anthony," And I'll get into actually a couple of those examples. But it doesn't mean that data science approaches and machine learning isn't attainable or isn't accessible for us. We just need to know a few things that we maybe don't think about when we're using like a traditional SIEM. One is, what's our goal? Are we detecting anomalies? Are we detecting relationships? We want to look at relationships in data, understanding our data, things like distant metrics, which we didn't have to think about in a SIEM, like L1 and L2 distances. I didn't know, 4 years ago. Is it numerical data? And there's a funny story. I was doing some k-means clustering, and I had put the source port as a numerical feature. And my data scientist that I work with says, "Hey, Anthony, that's a number, but it's not a numerical feature. Think about it's not continuous." And as soon as he said it, I realized it, and I said, "Right, that's a categorical feature that I need to convert." So things like that. When you're using binary features, like I'm using right now, I had initially tried the local outlier factor, and I kept on getting this message, this error in red here: user warning, duplicate values are leading to incorrect results. And I did some research and found out that LOF uses Euclidean distance by default in Scikit-Learn. And so the distance that it's measuring is between a 0 and a 1 and a 1 and a 0. And so it's going to run into problems because there's not really a distance vector there. And then choose your approach. Just like I said, LOF doesn't work. Default LOF in Scikit-Learn doesn't work with binary features. It can work, in PyOD. But again, choose your approach. Isolation force, we're going to go over PCA reconstruction. But there's other things, clustering. But I'll say it's not an easy button, right? You don't just throw data at it. And we're going to go through some actual data and some tuning that we've had to do and understanding the data that we're getting. And let me just continue with this. Okay, the first thing we're going to do is PCA reconstruction. And we're going to start with PCA, principal component analysis. Again, you're just going to have to learn, if you want to go down this road, a few things. And principal component analysis is a way to reduce features or dimensions, or if you're Excel spreadsheet, think about you got, 121 columns, like I said we had in this data set. And maybe we want to reduce the complexity or we have performance issues. We can reduce that with PCA and retain, as I like to kind of explain it, like we have a story and then we're going to write a summary. So I have this 500 book story, and how much of a summary do I need to maintain the actual story and the plot and the characters and the themes that are in the story? And this kind of tells us how much with a measurement called explained variance. And as we reduce the components, we see that the explained variance or the summary of the story kind of reduces. And the more the summary of the story reduces, that's going to impact our reconstruction. I'll get into in the next slide. Now, one thing I'll say is that I haven't found, and anybody that knows, please inform me, because I've talked to several data scientists, I've done a lot of research, but what is the best amount of explained variance? And for me, it's an experimentation from what I've grasped from other researchers. Somewhere in the 90 percentile is probably where you want to be. But I've noticed a difference from, in this example, from reducing the components of 14 from 90 to 30 components at 97. I've seen measurable differences even within the 90 percentile. So again, experimentation is key here. So now we're going to take those, we reduce the components, to somewhere in the 90th percentile. So now we're doing the Z part of the code up there, and we're doing the inverse transform, so we're reconstructing it to its original value. By doing this, after we do this, then we're going to take a measurement, and that's at a Euclidean distance. We're going to take a measurement of those two fields, those 2 points, and that's the reconstruction error. And the higher the reconstruction error, the more of it being an outlier. I'm going to show you some data in a second. But as we see here, the explained variance, as the explained variance goes down, so we're telling less of the story, the average recon error goes up. We end up having more outliers. So when we apply this to our data, we have scores. We have error scores, okay? We are making a subjective decision on which one of these we want to consider outliers. This is just principal component analysis and reconstruction is just telling us where the errors are at, okay? We set the threshold. So if I want to say 50%, sure, 50%. In this particular example, I said 1% are outliers. So I set the threshold at 99. And that red line shows on the left-hand side of that red line is 99% of my data. On the right-hand side of that red line is 1% of my data. And I'm saying those are outliers. And I can change that at any time. Once I go in and see the data and see what it's at. And if we look, here's a snapshot of a data frame here on the left. And it kind of aligns. 3.5 is my highest recon error, and we see that event over there at 3.5, and we see where the red line is probably about that 0.34 kind of area. So it kind of matches up with the chart. Again, these are subjective decisions. Once we start looking at the data and the results, we can make adjustments. The other piece we're going to be looking at is isolation for us. There's a few things that you need to learn. There's a lot of different parameters, but again, one of the most important one is the contamination, which is similar to the threshold that we had before. I'm starting with 2% on this. That means 2% of all the data that's returned will be the outliers. There's the in estimators, which is the number of isolation trees, and you can read up on isolation trees. And then there's the max features. We had 121 features. You could use a percentage of that to improve performance or add some randomness. You can also do some testing. If you wanted to get an idea of how many outliers you would get, you could just run the contamination through a loop. You can also run it through a grid where it would do a combination of all of your contamination in estimators and max features just to get an idea. For this, I'm sticking around with that kind of 2% range there. So now we want to look at what are our results? What does it look like? What does the data say? So to get this approved, one of the things I had to do was obfuscate some fields here. Apparently, Miles Davis doesn't work at Johns Hopkins, APL. But I replaced these. I'm a jazz fan, so I replaced the names with some jazz legends here. But the interesting thing is Miles Davis, who is actually the bad guy in this. So this data set was ran as part of a larger red team exercise. So although we don't have labeled data, we do have kind of the known truth by understanding what the red team was doing at the time. So it's interesting because in the PCA reconstruction, the activity that happened from the red teamers scored extremely high. One thing, the isolation forest, as far as high scoring goes, they didn't score Miles that high. The interesting thing is, as we see on the right, Wayne Shorter, one of the things I kind of didn't go over is working at a research lab that does cybersecurity research. I always joke because I say we have the largest legitimate Kali Linux install base that I know. And that means everything's an anomaly on our network, right? It's so by coincidence, this was an internal red team doing some testing on our identity that they let us know ahead of time, thankfully, but it caught them in this analysis. And again, they were just doing some testing, but it was really interesting to see them show up here. So from a high score perspective, but what if I look at all, because I know the ground truth, I can look at when I know that this red team was active in our environment within our identity platform. And when I look at it, PCA is extremely accurate at identifying the outliers. But we have some misses here with isolation for us. There's several events that it doesn't hit. So again, we set the contamination to 0.02 before. I can widen that net a little bit and see if that helps, and it does. And here at the bottom, we only have 2 that didn't hit in isolation for us. Problem is, with 2% contamination, we're already at over twice as many outliers than we are with PCA. And by increasing it to 4%, now we're even double of what we were previously. And that's not the direction. We want to balance how many outliers we're getting with, with what we want to use for analysis and how many of the known bad events that we're actually catching. So the other approach is let's combine these both PCA reconstruction and isolation for us as an ensemble approach. The top line there shows I'm just giving equal weight to both of them. The line underneath it, I've circled 98, which means that I have a combined score of in the 98th percentile. Once we do this, as far as what we're capturing here on the left-hand side, we're doing a little better than we are with isolation for us as far as high scores go, not as high as we're getting with PCA alone. And the chart at the right kind of just shows our outliers from both methods in the red there that are more extreme outliers. So this is the interesting thing. On the left-hand side, our numbers are a little higher. I would like to see them lower. But on the right-hand side, all the falses for isolation for us have now been turned to true by combining those scores, which is nice. So again, I go back to our Ensemble threshold, and we're going to tune this a little bit. And let's change that 98 to a 99. And our number goes back down to match what we have in our PCA. PCA and the Ensemble is very close. And then I look at all the data, and sure enough, all the Ensemble outlier data is true. So we've caught all the bad guys with the PCA and the outlier and the Ensemble methodology. So there's an argument. Well, PCA scored so high, PCA got everything, why use an Ensemble method? And a couple reasons. So one is you're not limited to 2. You can use 3 or 4, however many Ensemble methods you can. And although it didn't show it in this particular data, there could be the case that PCA didn't get it and isolation for us did get it, and then potentially an Ensemble approach could then turn that to an outlier. So you do have that, especially if you have like 3, you're going to have maybe you're doing KNN or something, and it gets some very different outliers that Isolation Forest or PCA wasn't able to get. And so I've seen that case before. So we went through this process. We started with raw data. We turned some columns into a single column in feature engineering. We did some, kind of cool time slicing. We prepped it for machine learning. We went through this entire process. We're getting roughly 10 to 15 results a day. And then that goes into some table somewhere. And, this gets into an entire philosophical discussion about whether these are false positives or not. I mean, because if there's nothing malicious going on, you're going to get 2% every day. So are they false positives? They're 2% of outliers. That's exactly what they are. And you kind of got to understand that from a different philosophical approach. Then I'm creating alerts, and I know that this alert fires on bad things, and it's a false positive, as opposed to these are outliers, and what do I do with them? And so from this perspective, if we're talking identity data, and let's just say our identity is our email, what do I do with it, and how do I pivot on it to look at other data types that may not be email-based or may not have my email in it? So this is where we can, pivot to LDAP and pull the user if we have the email. If we had the user, we could look for 4624s for all logins for that user to get a list of hosts. And then once we get that list of hosts, we can cross-reference those hosts to some of these other tables that I have on the right. And I make it sound really easy. But this is, I did want to say first that these Venn diagrams could actually represent like multiple tables. It could be like multiple sets of analysis that we have that we're feeding into kind of the category. Say for this one is FQEDN analysis, but we could have multiple different types of analysis. So now we're going to go back to hey, how do we get information if we just have the email? So I'm going to start with the light blue piece of code here where we have a data frame, and in one of the columns is email, and we can just, that would be step 1. And we're going to call this get user by email. And we're going to basically loop through every row and submit that email to a search filter, which is step 2, and then step 3. And I don't have all the code here, guys. I didn't want to saturate this with a bunch of LDAP queries. But basically, that search filter will feed the LDAP query, which will query LDAP and pull the user back. So step 4 now puts that user into a new column in the same data frame. Very straightforward, simple code. The second thing, now we have this column df user on the top. We can get a unique list of them, put them into a user list, which we then, however you want to format it, however you need to format it to, for whatever you're submitting it to. So this one, we're doing comma-separated values here. So we got Alice, Bob, Charlie. It represents our user string. So we pass that user string as a variable. Event code 4624s pulls all the workstation names for logins by that specific user. Now we have workstation names. Now we can cross-reference behavioral anomaly data and FQN tables that we weren't able to do with the email before. So it's not straight correlation. There's some Python that we have to submit in here. But again, very simple Python code, very simple approaches. That is my presentation. I think one of my themes here is I think SIEMs fall short. There's no state-based analysis. Looking at feature engineering types of approaches, deeper iterative data analysis where I can take data and feed it to a variable and then have that pass that variable to another search. SIEMs fall short of that. And I think things like Jupyter notebooks allow analysts to do deeper analysis of data. So my personal opinion, I think there's a skills evolution here. The bar is higher. Analysts need to think about things in more statistical ways. They need to understand ML language. I think it's core to modern security. When I think about dealing with very sophisticated adversaries, any alert that I get from a SIEM out of the box is not going to be helpful, because once I've investigated that and there's no more alerts, what do I click on? I think you need to be able to get deeper into data analysis. Easy buttons create atrophy. I've seen it. Analyst atrophy is real. What do? I know in a very specific case where a defense contractor got some CrowdStrike alerts. They investigated the alerts. They didn't know enough about a very sophisticated adversary. They ultimately pulled the box when they couldn't figure it all out, had it rebuilt. Unfortunately, the adversary had moved laterally before they pulled the box, and they were compromised in a bad way. And it's that, waiting for some, there's no easy button in cybersecurity, let me just put it that way. And analysts, as proof, I'm a huge supporter of red, blue, purple team types of engagements. I always say I don't give my CIO KPIs and KRIs. I give them report outs from red team engagements. I think that helps gauge how well your team's doing, especially from assume breach perspective, and also from a gaming the system perspective. So in this particular red team event, the system was gamed in the sense that the adversary wouldn't have been able to do everything they needed to do if we hadn't given them the access within the identity platform for them to carry out those actions. So, that's one of the things about cloud environments is their point in time, right? Any new configuration in any point in time can introduce a vulnerability that wasn't available the day before. So, approaching red team, blue team, purple team engagements with that methodology, I think, has been extremely important. And that's all I got, guys. Thanks for listening to me. And let me know if you have any questions.